Welcome to qnawire.
Okay, so for this problem, it says that a firefighting crew uses a water cannon that shoots water at a velocity of 25.0 meters per second. And we're given an angle of 53.0 degrees. Okay, so our initial velocity is going to be 25.0 meters per second, and our angle theta is going to be 53.0 degrees. Okay, so I have it drawn on the diagram right here. And we're also given that the firefighters want to direct the water at a blaze that is 10.0 meters above the ground. So we can use a Y value of 10.0 meters. Okay. So now it's asking how far from the building should they position their cannon. So the distance from the building we could represent as X here. So we're trying to find X. It also says that there's two possibilities, and can you get them both? Okay, so let's see if we get two possibilities here. Okay. So now the first thing we can do is we can break up the initial velocity into components. So let's get the x component of velocity. So it's just going to be v0 times cosine of theta because it's in the x direction. Okay, so I plug in v0 and theta. I'm going to get the initial velocity in the x direction. So I'll get 15 meters per second. Okay, now let's look at the y direction of the initial velocity. So it's going to be v0 times sine of theta because it's in the y direction. So I can plug in the value for v0 and theta. And then I'm going to get 20 meters per second. Okay. And now I could use kinematics to find the distance x here. But in order to find the distance x here, I'm going to have to actually know the time first. So I need to know the time that it takes for the water to hit the building here. So let's use our first kinematic equation here. So let's use this equation for the y direction. Okay, so I have this kinematic equation for the y direction. So I have y and y0 here, and I have the y component of the initial velocity. Okay, so now what I can do is I can plug in the values for these. And I'm going to get a quadratic then. So let's plug in. So we could assume y0 is the initial height, which can be 0. So we'll assume y0 is 0. So we know the value y, so we'll plug that in. So I'm going to get rid of the units now just so it looks simpler. So I have 10 for y, and v0y we computed to be 20 meters per second. So I have 20 t. Okay. And then, okay. So then I have 1/2 times ay t squared here. So ay is going to be the acceleration in the y direction. That's just going to be the acceleration of gravity, okay? Because you have gravity acting downward, so it's going to give an acceleration. So ay is going to be negative 9.81 meters per second squared, because that's acceleration of gravity. So I have a plus 1/2 times negative 9.81 t squared. Okay. So I can move the 10 to the other side here. So if I do that, I'm going to have a minus 10. And then this is going to be 0 on the side. Okay, so now I have a quadratic. So I can use the quadratic formula. If I do that, I'm going to get 2 values for t then. So if I use the quadratic formula, I'm going to get t let's see. So I'm going to get t is equal to 0.59 seconds. And I also get a value of t of 3.49 seconds. And again, we're getting 2 values because it's a quadratic we're solving. Okay. So now I have the time. So now what I can do is I can use another kinematic equation. So I can use this kinematic equation right here. Okay. So I'm using the same equation as before, but now I'm looking at the x direction. So anywhere I have a y here, I'm just replacing with an x. So the y and the y0 become an x and an x0. And the v0 comma y becomes a v0 comma x here. So I have the x component initial velocity now. And then the ay becomes an x. Okay. So now I can assume that the initial distance here, x0, is going to be 0. Okay, and I have the initial velocity in the x direction from before. And I know that ax is the acceleration in the x direction. Well, the only acceleration we have is gravity, and that x in the negative y direction, so it doesn't have an x component. So that means that ax is going to be 0. So we can mark this whole term as 0. So then we just have x, which is the distance, is equal to v0 comma x times t. So now what we can do is we can find the two distances we were being asked by plugging in the two different times here. Okay. So let's call this x1 for the first distance. So for x1, I'm going to plug in the v0 comma x times the first value for t. So let's actually label t1 and t2 here. So let's say t1 is the first time calculated. So it's going to be 0.59 seconds. And then t2 is going to be the second time, which is 3.49 seconds. Okay. So now x1 is going to be associated with the first time, t1. So I have the initial velocity in the x direction times t1. So it's going to be one possible distance from the building. Okay, so I plug in my v0x from the first page here, which is 15 meters per second, times the time t1. So if I compute that, I'm going to get a distance of 8.85 meters. So that's going to be one possible distance. Okay, so now what about x2? Well, x2 is going to be v0x times t2. So now plug in the same value for v0x, and I plug in t2 here, so I can get x2. So my x2 is going to be 52.4 meters. It gives me the second x value. So you may be thinking, how can we possibly have two distances that we could be away from the building and still hit the building with the hose or with the water stream? So now you can imagine that the building's here. So one possible scenario is the water goes like this and hits the building at a closer distance before it reaches its peak. Okay, so that's going to give us the first distance here. This will be x1. But you could also have the possibility where the stream of water is going to reach its peak and then start going down and then hit the building. So that would look something like this. So we'd have a stream of water and it reaches its maximum height and then starts going down again, but then it'll still reach the same height here. Okay. So these aren't quite proportional here, so let's actually draw this a little better, just to show that they get the same height. Okay, so you could have it so that the water goes like this, so it ends up being at the same height. Okay, so these heights here are the same, because the first example is when before it reaches its maximum height, and then the second example is when it reaches maximum height and starts going down again. But they could still be at the same height when it reaches the building. Okay. So that's how you can have two possible distances such that the water is going to reach the same height.